Welcome to today's lecture on IT security, and the topic of today's lecture is virtual private networks. So in the previous lecture we discussed firewalls, and by employing firewalls, resources in the intranet of an institution are protected against access from the outside. And what we deemed very worthwhile in terms of protection also turns out to be a problem for people working outside the institution. Think about sales personnel, think about technical personnel, whatever. People working outside of the institution that need access to the resources in the intranet are all of a sudden locked out from these resources by the firewall. So in the US, people working outside the company are often referred to as road warriors, being on the road, trying to fight for the company. But these people do not get access now to the resources in the intranet of the company, and that might be necessary. For instance, somebody working in sales might want to access the current database that contains previous offers to the company he is just visiting, or somebody in the technical department might want access to a certain documentation that is stored on a server in the intranet. So there are good reasons why people, members of the institution from the outside, might need access to resources inside the institution which are hosted in the intranet. However, they cannot get access due to the firewall. Well, for this problem there are a couple of solutions that could be employed, and in the good old days this was basically solved directly by using a direct remote dial-up connection through a modem, for instance, between the PC of somebody outside the company premises and a modem that was run by the company. But of course, this is costly and doesn't provide the right bandwidth, which is why this is not really an up-to-date solution anymore, although modems are still employed for remote management purposes. However, this is being increasingly reduced by the use of virtual private networks, which we're about to discuss in a bit. Another option that's possible is that all of the resources which are to be used from the outside are not shielded by the firewall, but are actually put onto the internet. So you could basically just switch and move the server from here to the demilitarized zone sitting somewhere here. It's not really depicted in that picture. However, there also is a problem with that approach, and the main problem is that if you have a lot of resources which need to be moved there, then that means that there are a lot of authentication mechanisms on the application and transport layer that need to be dealt with. If you want something like a single sign-on, might be possible to do this. However, if you want to check who gets access to your system, you would need to check the log files of all of the servers, whereas if I had a single point of entry, as we're going to realize with the virtual private network, it turns out to be much easier to check who actually gets access to what. So again, to sum up, dial-up is not really an option anymore, high cost, low bandwidth, and moving all of the resources which need to be accessible from the internet into the demilitarized zone does not really, or is not really practicable if there are a lot of resources that need to be put out in the internet. And basically also there is another point I should make here. You really want people working from outside the company premises, if they work for the company, to have access to all of the resources which they also have when they are within the company. That sometimes is difficult to achieve. However, in general, that should be the aim. So how can we deal with this problem? And the answer is to use a virtual private network. This here is the depiction of one type of virtual private network, so-called remote access VPN. What is a virtual private network? A virtual private network allows to run a secure, seemingly direct point-to-point connection between two stations, similar to a direct line between these two stations, by actually using a potentially unsafe, unsecure network as a connection media. So again, a VPN is a virtual, seemingly direct point-to-point connection which is secure between two stations, but it's actually realized by the use of an unsecure, potentially even unsafe network, such as e.g. the internet. VPNs can be realized in software as well as in hardware. And the question is, of course, how can you do this? Virtual private network, again, a virtual private network operates like a leased private line between the two stations. It is secure, however, we don't actually have a leased line. We are using an unsafe, unsecure network such as the internet to emulate a leased private line. And again, VPN also is secure. However, when we say that a VPN is secure, I just mentioned that the network which we are running the virtual private network over can be unsecure. It can also be unsafe in the sense that, for instance, the availability of the network is not guaranteed. And unfortunately, while there are means of guaranteeing the integrity and the confidentiality of information data being sent over a virtual private network, it's really hard to ensure the availability, particularly if we're using public networks that you don't have any control over whatsoever. That's an area where private lines are still better and also needed if you want to ensure the availability. How is this done technically? Well, technically, VPNs can be realized by means of tunneling and encryption. So this here is a depiction how a remote access VPN, such again as was depicted previously here before. So we have a machine that actually resides in the internet, but by the use of a virtual private network, this machine virtually moves into the intranet, and then once it's virtually part of the intranet, it can access resources in the intranet just fine, as if it actually is in the intranet. So how can this be done? Technically, and the answer is encryption and tunneling. Consider we have a client here, and this machine is supposed to be the client that is to use the remote access VPN in order to connect to the company. How would this work in practice? Well, this machine actually is not in the company's intranet. It sits somewhere on the internet, and since it sits somewhere on the internet, it would get an according IP address, because again, the IP address cannot be chosen deliberately. It pretty much depends on the network which the machine is in. So this is the internet IP address. What happens then is that the VPN, in this case software on the machine, would contact the VPN server that facilitates the remote access VPN, here in this case the server S, which also happens to has a certain IP address. Why? So what would happen is that this VPN client here would contact this VPN server. They would go through a handshake with authentication and negotiation of encryption credentials. So they would basically pick a cipher suit, pick a secret, and then go about encrypting all of the traffic between the two machines. And once this is set up, what would actually happen is that this VPN server here would hand out a VPN IP address Z to this machine. The address Z is an address that belongs to this intranet here, and all of the applications within this machine here would then use the IP address Z in order to communicate. So for instance, if they were to access the server W here, the application here would basically address the server by its IP address W, and the source address would be the address Z here. Now then, deeper down, we're going to see this in the networking stack. What would happen is that this IP address Z, since it's actually an IP address belonging to here, it cannot really be used from this position in the intranet. So what happens then is that the VPN software would basically take the packet that was created from Z to W and encapsulate this packet, which means encrypt it and put it into another packet, which would then be sent to the VPN server. So we would see a packet from destination IP address, or depending on how you see it, destination IP address X, and or the source IP address X and destination IP address Y, and in the reverse direction, of course, the address is just interchanged. And the server would get this packet, decapsulate the packet, and send it in the clear on the wire in the intranet. So then we would again see the packet to W from IP address Z, and of course the corresponding payload on of the packet. So let's go into the networking stack and let's look how this looks into our reference model. So here we have the depiction of our scenario in the network reference model that we typically use. So what we really have is here is our client, the client that wants remote access through the VPN. And again, this client is going to use the virtual IP address from the intranet up to here, and then somewhere, and again, this depiction from the reference network can actually change depending on the type of technology which is used for creating the VPN. So what happens then is that from this point on here, the packet is being encrypted and encapsulated into another packet. Then this encrypted and encapsulated packet is sent through the network to the VPN server, where the packet again is decapsulated and sent on. So virtually, this is the actual position of the client here behind the VPN server. And then there is a connection between here, and that connection again is not subject to the encryption of the virtual private network anymore. What, of course, the server sees is it sees a machine that comes from the intranet, and again, the reverse connection is facilitated by the VPN server picking up all the packets which are destined for the client. Then the packets are just as before encrypted and sent on to the actual IP address the client resides at. So what you see here is that the pink part of the connection here is the encapsulated and encrypted part, and that's also where you see that this here is the public network. The connection here is encrypted, which basically means its integrity and confidentiality are preserved and ensured. And from this point on, the client basically sits in the intranet, which basically means that the public network here is used to create a virtual point-to-point connection between the router and this machine here. This is basically what this picture is also intended to show. Now, one thing on that should be mentioned is that the VPN tunnel here, which is present if there is a contact between a server and a client that comes through or uses VPN, then for the server, the use of the VPN is completely transparent, which basically means that if there is, as depicted here, let's say HTTP connection between this machine and this machine by use of the VPN, the server here has no idea that the machine that is contacting it is coming through a VPN tunnel. So far so good. That was a so-called remote access VPN. Let's move on to another type of VPN, the so-called site-to-site VPNs. So again, that is another depiction of remote access. Let's move on to site-to-site. VPNs cannot simply be employed to guarantee a safe and secure seeming direct point-to-point connection between a single machine and a gateway. VPNs can also connect two gateways with each other, and this is shown in the example depicted up here. So what you see here is a company, and this company has a site A and the company has a site B. And of course, both of the sites are connected to the internet, as you can see here, but it is very obvious and not far-fetched to think that, of course, each of these sites might also have resources that need to be accessed from the other site. And in previous or in former times, what needed to be done is you went to a service provider and leased a private line for connecting the two sites with each other. This was very expensive, and with the use of VPNs, which basically allows for a cost saving, you could connect the two sites by a virtual private network instead of an actually leased line. And how this can be done is shown in this depiction here. So what we see here is we see two machines, R1 and R2, and these machines want to communicate with each other. So R1 wants to send a packet to R2, and we now assume that these two sites are connected by a site-to-site virtual private network. How is a site-to-site virtual private network really implemented in practice? Well, you have a gateway here and a gateway on the other side, and these two gateways basically set up a VPN tunnel between each other. So basically what happens here is that due to the configuration, this machine knows that everything that is destined here for this intranet site basically needs to be encapsulated or encrypted and encapsulated into a packet that is then going to be addressed to G2. Once the packet arrives at G2, of course, all of this is based on authentication that happened previously. Packet is being decapsulated and sent on to R2 again. So if R1 now sends a packet to R2, what happens is that R1 generates a packet destined to R2, source R1 with a payload. Packet travels to here. Here the packet is actually encrypted and encapsulated into a packet that now is destined to G2, and source is G1, and within this packet we have the encrypted original packet. Here it's being decapsulated and then being sent on to R2. So if we use such a site-to-site VPN, then again, neither R1 nor R2 have any idea that there is actually a VPN going on between the two sites, where they only see that they can connect another machine. They have no idea as to how the connection is actually facilitated or whether this connection is going through a VPN or not. That is important in the sense that if VPNs are employed, it's not necessarily the case that the end users can rely on a VPN being present or their data being protected somehow. So if R1 wants to send something that is confidential to R2, it is mandatory that also some end-to-end encryption between R1 and R2 is set up in this case in addition to the VPN, but as viewed from R1 or R2, they don't know that there actually is a VPN, so they need to set up some security mechanisms. So in the following, we are going to look into two particular types of mechanisms how VPNs can be implemented in practice. And the first we are going to deal with in quite some detail is IPsec. IPsec, IP secure, is specified in IETF RFCs, and IPsec does not only deals with VPNs. In general, IPsec offers security services on the IP layer and works with IPv4 as well as with the new IPv6 protocol, which is likely going to replace IPv4 in the midterm. Don't want to say any more about IPv4 versus IPv6, but IPv6 has been around for quite a while, and basically IPsec follows the terminology and idea of IPv6, however, can be employed with IPv4. IPsec is connectionless and contains two different types of security protocols, in particular authentication header, for short AH, and encapsulating security payload, ESP. Those have been specified in RFCs, and systems which implement IPsec must also implement ESP. AH, the authentication header protocol, is however optional. Authentication header allows for the authentication of the sender and to ensure the integrity of protected packets. However, there is no encryption with authentication header. Encapsulating security payload allows for the authentication of the sender, the integrity protection of packets, as well as encryption. However, the integrity check with ESP is a bit less than what authentication header offers, which is why it is possible to also use them in combination. Both protocols allow a somewhat limited protection against so-called replay attacks. What is a replay attack? Well, basically, a replay attack is an attempt of an attacker to record a legitimately encrypted and transmitted packet on the wire or whatever medium you use, and then replay that packet later. Without replay protection, this packet, which is transmitted later, of course, seems to be okay. In fact, it is okay. The only problem is that this packet has already been processed and was sent previously. And if there is no replay protection, replaying packets which have already been there can lead to quite severe consequences. So the protection against replays is an important aspect of security protocols. For instance, by replaying packets, in the worst case, that packet might contain some type of command, and that command might be then executed due to the packet being seen again. Or, of course, if you get the packet, then you need to decrypt the packet and you need to process the packet, and then maybe you find out it belongs to a connection that's already gone. However, you need resources for the decryption, and that in itself can give rise to a so-called denial of service attacks, in which basically resources in the systems which are using the tunnel are being exhausted. So again, both protocols offer a somewhat limited form of replay protection as well. Basic foundation of IPsec is the concept of a so-called security association, which is a unidirectional, you can say it is a contract between two stations, which basically tells the stations what to do for the security associations, and each security association either uses ESP or AH. And in practice, of course, we are not using unidirectional security associations, but you always would have security associations in both directions simultaneously. How do you establish a security association? Well, that could of course be done manually. However, there also is a so-called Internet Key Exchange Protocol, which can be used for establishing a security association. The Internet Key Exchange Protocol allows for the exchange of keys and the authentication of stations. And again, if you use that protocol, what you end up with is 2 security associations, one in either directions. Security associations and their configurations, and there are numerous options on which configurations can be used, are stored in a database, the so-called security association database, and the security associations can be uniquely determined taking into account IP source address, the used security protocol, and a so-called security parameter index, which is a 4-byte value that is chosen to distinguish between security associations with the same destination and the same security protocol, as of course there might be multiple and numerous. These informations are included in each and every packet that's being transmitted, which means that for a packet that comes in through ESP or AH, you can basically determine to which security association the packet belongs to by contacting the security association database, and then you know what to do with the packet and how to, for instance, decrypt it or check the integrity of the packet. IPsec also has a so-called security policy database, and in that policy database, which is akin to the rules in a firewall, it is possible to specify so-called selectors, such as, for instance, the IP address of the peer station, and by looking into these selectors, you basically check whether for a particular packet which is incoming or outgoing, the packet needs to be protected by IPsec, needs to be just sent through without IPsec protection, or whether the packet must be discarded. So in that sense, if you have a machine that supports IPsec and is doing something, then as you have seen in the previous examples, not all of the packets flowing through the machine must be then encapsulated and encrypted and protected through a particular IPsec mechanism. And again, there might be numerous mechanisms. In fact, just as for a firewall, a packet would traverse the SPD, security policy database, and then would be determined what to do with the packet, and that might also include not giving it any IPsec protection at all. Security associations can operate in one out of 2 modes, so-called tunnel mode or transport mode, and we'll get into these modes in a second after looking into where IPsec actually resides with respect to the protocol stack. And this is depicted here. As you see, we have the transport layer, and then as interface to the network layer, we still have IP, and then below that there is IPsec protecting IP packets which are being processed on the machine. So IPsec sits somewhat below the IP protocol in the network layer, if you will. And then, of course, whatever has been protected by IPsec or not is handled to the data link layer, and the reverse process happens if data comes in through one of the data link layer protocols. Okay, so coming back to the different type of modes, tunnel mode or transport mode, these modes have different characteristics. In tunnel mode, what happens is that if there is a security association between 2 stations in tunnel mode, then all packets which are being secured by the security association are being tunneled between the stations, which basically means that the packet to be secured through the association will be encapsulated in another IP packet. So there is a new IP header and then being tunneled between the systems. The IP source and destination address are the addresses of the systems which are being connected by the security association, and they are then, of course, being transferred to the respective station where decapsulation and integrity and or encryption and or decryption, integrity check and or decryption takes place, and then packets are forwarded on their way. So that's tunnel mode. There also is a mode called transport mode, And in transport mode, basically IPsec supports end-to-end encryption of packets. And in that mode, the IP header of the protected packet, particularly source address and destination address, are not changed through IPsec. There is no new header, no encapsulation if you want, but actually the payload of the packet is processed by IPsec and either integrity protected or encrypted. However, of course, this cannot be used for VPNs. If we want to create a VPN, as we've outlined, either for site-to-site or for remote access, what we typically use is encapsulating security payload in tunnel mode. However, it's worthwhile to also take a look into authentication header because the protocol is somewhat simpler. How does the authentication header protocol look like? Well, here is the header of the authentication header protocol, and the AH protocol type field is 51. In the header you see a couple of fields as depicted here. There is a next header field. This is again akin to IPv6, where basically the original header fields of IP have been split into a lot of optional headers which may or may not be present, and whatever is present next is then indicated in the next header field. This has also been used for IPsec, of course. So there is a next header field, there is a payload length field, which is the length of the AH header in 4 byte steps -2 for technical reasons. Then you have 2 bytes which are still reserved and not yet used. There is the security parameter index, which I already indicated. That value, along with the IP address and the use security protocol, allow for the unique determination to which security association such a packet belongs. There is a sequence number. That sequence number is used for replay protection, and again, sequence number, please note, we have a connectionless protocol. There is no retransmissions of anything that has been sent out and not made its way through the network. The sequence number solely is for replay protection. The sequence number starts with all zeros, and for each packet which is being sent for the security association, the value is increased by 1. Once the maximal value has been reached, a new security association must be set up. It's not possible to roll over and restart with 0. Since there are only 4 bytes present, the length of the security of the sequence number might be too limited, which is why it is possible that when a security association is established, to negotiate for an 8-byte long sequence number. If this is the case, then only the last 4 bytes are actually transmitted, and the first 4 bytes are not really transmitted, but only taken into account for generating the checksum in the integrity check value, which has variable length and comes here in the next field, and basically contains the integrity check value for the packet which is being transmitted. This field is variable because it pretty much depends on what type of algorithm is used for integrity checking. It always has a length of 4 bytes, and if necessary, padding is used. Depending on whether AH is used in transport mode or tunnel mode, a structure of a packet can differ or does differ. Here you see association header in transport mode. What happens is, of course, that the IP header pretty much remains unchanged, and between the payload and the IP header there is the authentication header, which contains the information just discussed. If we are using tunnel mode, then something else happens, because basically there is a new IP header, and then we have the authentication header field, and then we have the original IP header, and then the data. So that should be pretty straightforward according to what we discussed before. Again, tunnel mode is what's being used for actually setting up VPNs. Alright, let's move on to encapsulating security payload. Encapsulating security payload doesn't only allow for integrity and authentication, it also allows for encryption. The protocol allows for the use of different types of mechanisms for integrity check and protection. It can also allow for them separately with different algorithms. However, typically ESP is used to check for integrity and confidentiality at once. IP packets which are protected by IPsec and ESP get protocol number field or have protocol field number 50, and the header for ESP is depicted here in the picture you see. I don't want to go into all of the fields. You can see that they are basically very similar to what you've seen in authentication headers. So there is a security parameter index, a sequence number, and what you see here is basically for the encryption part, where we have, of course, well, an initialization vector, we have payload data, we have a so-called TFC padding. TFC stands for traffic confidentiality padding, and that allows to basically randomize the size of the packets which are being transmitted. Then there is actual padding, the length of the pad, and a next header field, which of course sometimes is also used. ESP can also be used in transport mode and in tunnel mode. Both are pretty much straightforward. So here you see ESP in transport mode, and here you see ESP in tunnel mode. How can I set up security associations, and how can I actually manage keys? Well, IPsec allows for two means on how to do this. One is just manual methods, and for manual methods, basically you already put manually all of the credentials in to set up the security associations by hand. That's all good and well, but if you keep increasing the number of systems that you take into account, then that becomes tedious at some point, which is why there are automatic methods for setting up security associations, managing security associations, and handling them. And one of the means on how this can be done, and also one that scales well, is a so-called IKE exchange, Internet Key Exchange Protocol. It basically is a standardized method which can be used on numerous platforms and between different institutions as well. It scales well, it is highly automated, and it can create security associations on an as-needed basis. The Internet Key Exchange Protocol allows for the mutual authentication of communication peers, and of course to also set up a so-called Internet Key Exchange Security Association, which can then be used to derive security associations for IPsec from this. This also includes the generation of cryptographic keys and the negotiation of the respective cipher suits which are necessary. The protocol is very, very simply specified. There always is an Internet Key Exchange request, which is entered by an Internet Key Exchange response, and all in a request with the following response is called an Internet Key Exchange. This is the general header field. I don't want to go into the details of the header fields. You find all of the details specified in the RFC for the Internet Key Exchange Protocol. However, of course, there are SPIs, which are fields that uniquely identify the initiator and the responder, and these values can basically be randomly chosen, but then they are later used to uniquely identify the stations which communicate with each other. This is of course just the header. The type of payload that's then in the packet is specified by the next payload field. IKE is supposed to change, which is why there is a major and a minor protocol version. There is a so-called exchange type that specifies what type of exchange is going on. You see that field here. And for instance, this can be an Internet Key Exchange initialization, can be authentication, and other things. There are also flags, and there also is, that's important, a message ID, which is basically mirrored in order to identify a request and the corresponding response. So that was a very brief walkthrough on IPsec and the related protocols. You are very welcome to play around with IPsec and IKE in the laboratory. It is very worthwhile, and what's also good is that since all of the standards are open and specified in RFCs, you can pretty much take a look into all of the specifications and find out what these protocols are doing in great detail. So, when we create an IPsec tunnel between two machines, like in this example, which is pretty much the practical example that we're going to use in the lab and later, then we basically have a tunnel, and the traffic you will see here in this network. If we have two routers, one here which connects the 192.168.10/24 network to the public 172.16.20/24 network, and another router that connects the public network here to the private 10.2.40/24 network. If we now establish an IPsec tunnel between these two routers, then within this network we are going to see AH or ESP traffic, we assume tunnel mode, between, of course, this IP address 172.16.24 and this IP address 172.16.25. And basically, after setting up IPsec correctly, as if you remember in our layered model, IPsec sits somewhat below IP. There is not much that otherwise has to be done, because basically once it's determined that the packet's supposed to go there and the database is being consulted, then the packet is going to be encapsulated and be sent on. Let's look into one more technology for creating VPNs, which is OpenVPN. OpenVPN is available for a couple of operating systems, among them Windows and Linux. And while IPsec is limited to receiving and transmitting data on the networking layer, OpenVPN is a bit more flexible and can operate on the networking layer as well as the data link layer. We'll discuss different types of VPNs and how to classify them later on. So there are also other differences. Again, IPsec is using as protocols AH and ESP. For OpenVPN, there really is no different protocol, but what actually is used for transmitting the data between the two endpoints is a protocol UDP or TCP and TLS SSL. So we will get to know TLS SSL in much more detail later. However, suffice to say right now here that it's really a layer 4 transport layer technology for authentication, confidentiality, and integrity, and in that sense does not really appear like a real VPN technology. So how would OpenVPN work? Well, again, just said that if you go back to the picture here in IPsec, there really isn't much to do. OpenVPN works by creating virtual interfaces in user space. Under Linux, this is either a TAN or a TAP device. And in a similar scenario to the one which we just illustrated for IPsec, what would happen with OpenVPN is that you would basically set up two new virtual interfaces here, which are point-to-point interfaces connecting the two routers here. So this is how OpenVPN would actually display on the routers. You would basically see a point-to-point connection between the two routers here. Of course, in fact, there is no point-to-point connection. This is a virtual point-to-point connection. What really happens is that if something is sent to the virtual interface, while it appears that it's sent through this virtual connection, it in fact is encrypted, encapsulated, and sent over the public interface here. That's how OpenVPN is actually operating. So to make this clear once more, for OpenVPN, again, we have virtual interfaces on both sides, and the OpenVPN tunnel displays like a direct point-to-point connection between two new virtual interfaces. This is at least exactly true if we are using VPN, OpenVPN with a so-called TAN device. We're going to look at this later in some more detail. So again, OpenVPN uses as actual transport protocol TLS-SSL, and it can be run with TCP as transport protocol as well as UDP. That may sound a bit surprising to those of you who have a bit more intricate knowledge about SSL-TLS, because basically SSL-TLS requires a reliable transport connection, aka TCP, and it was originally designed for TCP, but exactly for OpenVPN, SSL-TLS has been modified to also be useful in connection with UDP as a transport protocol. UDP as a transport protocol, of course, makes much more sense when it comes to VPNs. Why? Because basically if a single packet or frame or whatever is not received fine at the other side, you don't really want to stall the whole transmission until that frame has been retransmitted. You want to go on sending out packets, which is why UDP is likely the best possible choice for doing this. So again, OpenVPN is fairly flexible and can forward traffic either from the networking layer as well as the data link layer. And if OpenVPN is used on the networking layer, a so-called TAN device comes into play. If we use it on the data link layer, a so-called TAP device is used. Well, this of course is only the appearing situation. What happens in reality is depicted here. If something is sent to the virtual interface, then whatever goes to the virtual interface in the machine here is actually being given to OpenVPN, handled there, and then forwarded, of course, encapsulated, encrypted through the public network to the endpoint B, where again OpenVPN gets the data, decapsulates and decrypts, and also introduces it through the user space interface TAN or TAP device into the endpoint B. So that's what actually happens when OpenVPN is used, and we just saw what it looks like in terms of from the conceptual situation. All right, so let us look into the actual practical application of IPsec, and we are going to illustrate this by using a lab example which also takes place in the reference network that you're already familiar with from the experiments we conducted, for instance, on firewalls. So within this scenario, we've again prepared a couple of machines that we are now going to go through. So basically what we have is we have two internal networks. Again, we have an institution network 192.168.10/24, and we have an institution network 10.240/24. Both of these networks are connected to a public network, which is the 172.16.20/24 network. So there are routers within both of the networks that connect those networks to the public network. And again, we can take a look at the individual machine in these networks. What we are going to do then is we are going to establish an IPsec connection between this router and this router in a site-to-site configuration, and we're going to check out what's going to happen to the traffic that is being sent through the virtual private network, which is based on IPsec. But before we do that, let's just take a look into the usual scenario that you're already familiar with. So let's take a look regarding the router. This here, let me switch to the machine. This is the router that connects the 192.168.10/24 network to the 172.16.20/24 network. And let us also check out the other router here. So this is this machine, the red background, and again, machine has two interfaces and just sits there. We have a server here at 10.24.37. Let me switch to this machine. This is the server, and what I'm going to do, it's also something you're already familiar with. I'm going to start an HTTP, basically a process that is listening for incoming HTTP traffic on port 80. So, okay, process is started, and going back to the picture, we've seen this machine, we've seen this machine, we've seen this machine, and you guess it, we're also now going to go to the client and going to check whether we can connect to the server here. But before we do that, there's one thing missing, namely we are going to take a look at the traffic here on this public network. And for doing this, I've also configured a machine which sits in this network in promiscuous mode and is able to listen to all packets that are traversing this network, and this machine is shown here. IP address and so on and so forth doesn't really matter. Only thing that matters is that we are going to start a sniffer on this machine based on Wireshark. That is basically also just checking out what type of traffic is coming through the network. So again, we run our sniffer here in the network. We've started a server here. Now we're going to go to 192.168.1.100 and we're going to start a client that connects to the server. I'm going to use Firefox for this, and you already know the InfoSocket server, so you know what to expect when I'm accessing 10.2.4.37. What we see, yes, is basically just the connection information as usual. Let's check what we observed in the public network from this. I'm stopping the capture here, and well, it's basically what you would expect. We see TCP HTTP traffic from 192.168.1.100 to 10.2.4.37, and again we can check what was actually transmitted, and you see here that this transmission happened in the clear, so we're able to read all of the conversation going on between the client and the server. In this case, it's a sort of mock-up HTTP/HTML conversation. So let's restart the capture. Okay, capture is running again, and what we want to do now is we will do the same experiment, but the difference is that we are going to establish an IPsec tunnel between this router here and the router here. So we are now going to use IPsec to create a site-to-site interface between 192.168.10/24 and 10.2.4.0/24. So how do we do this? Well, obviously we need to configure both of the routers here accordingly, and let's just start with this router and by checking out which files are to modify and how. Of course, we've done this before. The important file for the configuration of IPsec in the version I have here on this machine is the etc ipsec.conf file, so let's take a look at that. Here we have it. So what do the individual lines here mean? It's a bit minimalistic. So we have a name for the connection here. The type that we want of connection is tunnel. We are gonna authenticate by using a shared secret. I can take a look at you can take a look at the secret in a second. You see here that left specifies the left endpoint of the IPsec connection, which is the machine 172.16.24, and the subnet which is connected to the left machine is the left subnet 192.168.10/24. So that's exactly where this machine sits. So left is the machine itself. It connects to the machine right, which is 172.16.25, and the subnet connected to machine right is 10.240-20/24, and we are going to start this IPsec tunnel automatically. Why are we using left and right instead of let's say this and other? Well, the reason is that by using this configuration file twice, it would actually be possible to run the VPN as well, because IPsec has some smarts built in that would allow for that. Let's take a brief look at the shared secret we use. It's stored in IPsec.secrets. Here we have it. It's a PSK, which stands for pre-shared key, and it's basically the key which is then enclosed here within. So gemeinsames Geheimnis is the key we're using. Okay, how do we start IPsec? Well, basically we have to issue a command that would use these credentials and set it up. I'm going to do this in a bit. Let's first take a look at the other router. So what you see here is we've actually interchanged left and right. Other than that, it's pretty much the same. Let's also take a look at the secret. And as you can see here, it is of course the same secret. Now that should not be a lot of a surprise. Of course, if you were to use different secrets, it wouldn't work. Okay, so again, we've seen the configuration here and here. The only thing that remains to do is to actually start the IPsec tunnel, and this can actually be very simply done by the command sudo IPsec setup start, but for the reasons that this is a bit more versatile, I've scripted this. So with the command start IPsec demo, I can start the IPsec demo. Okay, start it on this machine. Let's start it here. Started on this machine. So now IPsec was started on both of the machines, and again in this configuration we are sniffing here in this network, and what you already see here is you see key negotiation going on, while the actual negotiation is beyond the scope of this lecture. You see here that the ISA KMP identity protection is used, and that this is basically here the connection negotiation. Let's also create some traffic now, and let's do this by basically connecting from the client to the server again. So I'm gonna just reload a couple of times. You see there's a new connection happening, and let's check server side that all of this was received fine. Yes, you can see this here, and let's take a look at what we sniffed in the public network. And as is to be expected, we are observing ESP traffic here, so we are using the encapsulating security protocol as was specified before. Just a couple of things that I would like to point out here. First thing I would like to point out is that you should please note that since we are using a site-to-site VPN, we are no longer observing a connection between the two endpoints which are actually involved in the connection, but what we rather see is ESP traffic between the two gateways which establish the IPsec tunnel. This is of course to be expected because we are using encapsulation, and what we see is traffic between 172.16.2.5 and 172.16.2.4, or vice versa, of course, using ESP. We can no longer check what happens here. If I'd like to follow the TCP stream, you basically would see that what I see here is not readable because it is actually encrypted. Of course, this being not readable is not a proof for encryption, but we will leave it with this for now. So that basically shows how IPsec is working. And again, we see ESP, which is a protocol on the networking layer and part of IPsec, and this is flowing between 172.16.2.4 and 2.5. So if somebody were to observe here in the public network, as we actually just did, what we will see is we won't see traffic between the two endpoints here, 192.168.1.100 and 10.2.4.37. We will only see traffic between here and here within the tunnel. So that pretty much concludes IPsec. Let's move on to OpenVPN. So for doing this, I'm stopping the IPsec demo first on this router and here as well. Okay, IPsec is stopped. Let's briefly check this by running a connection a couple of times and see what we get on the public network here. Let's start the capture and check what's happening. Yeah, you again can see the traffic in the clear, so the IPsec VPN is stopped now. Alright, so let's move on to using OpenVPN. So again, for OpenVPN, what we actually do is we are creating a virtual interface either on the data link layer or on the network layer, and then we are using SSL TLS to actually transport the traffic through the unsecured network. So that's again the picture what happens conceptually. What you're going to see is you're going to see a virtual connection between here and here. And what of course then really happens is if something comes to the virtual connection, it's encrypted and encapsulated and then actually sent through the real interface through the network to here, where again OpenVPN takes it and sends it to the virtual interface. So you remember this depiction from a couple of minutes ago, and now we're going to see how this actually works in practice. So we're going to set up the same scenario as before, namely a site-to-site VPN in the very same network that we were just considering. However, with OpenVPN, things again work a bit differently because two virtual interfaces are involved. And what we will do is we are going to create two virtual interfaces, one on each of the machines, and then we are basically going to use those virtual interfaces for communication between the machines. So let's take a look at how this works in OpenVPN, and again we're going to check out the configuration on the respective routers. Let's first start with this side here. For using OpenVPN, basically we have to identify one side as the server side and one side as the client side. That simply has to do with the fact that for SSL TLS we need a client and a server. Really and also we're going to use TCP, I should add. Really that doesn't make much of a difference, and basically it's just the question which of the machine waits for the incoming connections and which of the machines is going to then initiate the connection, and we arbitrarily decide that this machine here is going to be our server side. So let's take a look at how the server configuration actually is done and what the configuration files look like. I've changed to the machine, so let's take a look at the configuration file, which now is under demos. This is the configuration file. Let's take a brief look at what the individual entries mean. Dev10 says that we are going to use a TON device, and again this means that we are going to handle data from the networking layer. Proto TCP server specifies that we're going to use TCP as protocol, transport protocol, and that this machine here is going to be the server. This is also specified by TLS server. If config 1099.99.1, 1099.99.2 basically specifies that we are going to create a point-to-point connection as specified before between these two IP addresses. So on our side we are going to assign the address 1099.99.1 to the interface, and the point-to-point link is going to go to interface 1099.99.2. The other entries basically specify all of the certificate credentials and private keys which are necessary for establishing a TLS connection. So basically CA here specifies the certificate of the CA that was used. With cert we specify the certificate of the very machine we are at. So this is the certificate of our own machine. Key is the corresponding private key for the public key given in the certificate. And the other thing we need for OpenVPN is we are going to enter a Diffie-Hellman exchange, and parameters for the Diffie-Hellman exchange are stored in this file here. Let's take a brief look at how this looks on the quote client side unquote. So here is the router, more demos config. Yeah, pretty much similar. You see again the TON device, TCP client, TLS client. That again is to be expected. Basically this is what we had before, just server replaced by client. Since the client initiates the connection, I also need to give the IP address of the machine which we are going to establish the OpenVPN tunnel to. This happens to be 172.16.25. And then again we have the mirrored if config command as from the other side, and we again have the corresponding certificate credentials. Well, so that's basically all there is to say. The only thing we need to do now is we need to actually run OpenVPN, and that's what we're going to do. I'm going to start on the server side. I'm sorry, that was the wrong machine. Here we have it. Start OpenVPN server. I need to enter the password for the private key because it was password protected. That is not typical, but we've configured the machine like this time. So now the server is running. Let's start the client as well. Start OpenVPN. I again have to enter the password for the private key on this machine. And basically, well, that's it. OpenVPN is running. Well, before we are going to check what happens to the traffic, let's take a look. I've mentioned that we've created TON devices on both machines. Let's take a look here. We should have created a device called TAN0. And here we take a look at the configuration of this device. What you see here is we have on the client side a TAN device with the address 10.99.99.2, which is a point-to-point connection to 10.99.99.1. And it is, of course, not too surprising that if we were to look at the other router now, we would see the same exactly reversed. Let's take a look anyhow. Well, as you see, 10.99.99.1 to 10.99.99.2. So, okay, everything fine. OpenVPN is running and the devices are configured. Let's take a look at what happens if we are sending traffic from the endpoint 192.168.1.100 to the server from here to the server here. Let's do this. Before I do that, let's start our sniffer in here again. I think the sniffer is already running, but it probably makes sense to just restart. Okay, and now let's quickly do one connection. Okay, fine. And what do we observe here? Well, that might look a bit surprising to you, but obviously none of this traffic has actually entered the OpenVPN tunnel. All of it was transmitted in the clear. We can again just see what happened here. So that seems surprising, but it's very simple to explain why this behavior occurs. What we've done so far by setting up the OpenVPN is we've created a point-to-point interface between here, or a point-to-point connection between here and here. But of course, since we didn't make any changes with respect to the routing, these machines now just have an additional interface which isn't used for much. We can actually check whether it's used for anything or not by looking at the route command. Looking at what's happening here with the route command, and what you see here is, well, we have the destination 10.99.99.1, but the only thing that's being sent there so far is everything that's destined to 10.99.99.1 itself. Everything else, as you see here, without going into too much details, still run through ETH1 or ETH0. So if we want to make use of our newly established tunnel, we must change the routing accordingly, and that's what I'm going to do. Take a look. The most important entry we have is the entry here, which basically says that if I want to reach the 10.2.4.0 network, I'm going to use 172.16.2.5 as a router. So first of all, I'm going to delete that entry. Okay, entry is deleted, and now I'm gonna add another route that says that everything that is destined to this network from now on is supposed to go through the gateway 10.99.99.1. Okay, excellent. Let's do the same on the other router. So in this case, of course, we need to delete the route to the 192.168.1.0 network. Sorry. And we need to add a route to this network by using the gateway. And again, now we need to just mirror what's happening. Anything which we want to route here must go through 10.99.99.2. Good. So far so good. So now we've adjusted the routing tables. Let's just take a look at the routing table again here. So this is our new routing table. Looks good from here. Let us restart our capture now. And let's again establish a connection from the client to the server. Okay, happening. Let's take a look at what we've observed. Well, yes, we see traffic between 172.16.2.5 and 172.16.2.4. The type of traffic we see is TCP traffic, and that's of course good and well because SSL TLS runs over TCP. And as you see here, it's going to the open VPN port or coming from the VPN port server side. And this again is traffic which is going on layer 4 from the respective machine, one of the respective machines to the other machines, and then of course in the reverse direction. If I now go on follow TCP stream, what you see here is you don't see much that is useful, as is to be expected. So pretty much the same scenario. We see traffic between 172.16.2.4 and 172.16.2.5. Please remember that of course none of the virtual IP addresses of the virtual interfaces will ever show up in a connection like this. This should be perfectly clear to you because basically if any of the virtual addresses were to appear, then something must be terribly wrong because nobody in the network actually knows where these addresses are, and these interfaces are just virtual interfaces which don't really exist. Okay, so we see what is about to be expected. TCP SSL TLS traffic between 172.16.2.5 and 172.16.2.4. So while we've studied site-to-site connections thus far, we're now going to take a look at using OpenVPN for RAS configuration, and we're going to change the scenario as follows. Instead of creating a site-to-site VPN here, we are creating a remote access VPN from the client to the router on this network. And again, we are going to do this by using a data link layer connection, which basically means that these interfaces here will not have assigned their own unique IP addresses, as you're going to see in a second. For doing this experiment and starting in a clean state, I've restarted both of the routers, so there is no OpenVPN running anymore. Let us briefly check by that we are in a clean configuration by restarting the sniffer here and by creating a couple of connections and checking what we observe. All good and well, no more VPN running. So now what we want to do is we do want to create a VPN, open VPN between the client on 192.168.1.100 and the router into network 2. So let us take a quick look at the respective configuration file. Sorry, let me quickly check this. So that file should look familiar to you. We now have a tap device. Again, this is the server, and we're again using TLS and TCP. And you see a bunch of certificates, which is basically not very different to what you've seen before. Let's take a look on the client side as well. that also isn't too surprising. We basically also have just the change that it's a tap device this time, and again the remote address of the VPN is given, and of course the necessary keys are specified. So of course this is not all. There are a couple of other things which are necessary, and let's first take a look at what we have else on the client side. In order to start, we are going to use this script. What it basically says here is we are going to start OpenVPN, and we are going to use a tap device, and that what we need to do is we need to bring this tap device up, and what we also do is we are assigning an IP address to this tap device. Remember, this is basically a layer 2 device like an Ethernet interface, and then we are going to start OpenVPN. So what we do here on this side is we establish a tap device, connect OpenVPN to it, and assign an IP address, namely the IP address 10.242.1.2 to the device. So as you see here, the address 10.242.1.2, as you see here, is from this network, of course. So if you remember what we discussed earlier, this machine virtually is tied into this network. You might ask yourself, how is this done on the server side for OpenVPN? Let's also briefly check this by looking into the respective file as well. Here you see, again, we are creating a tap device, and what then happens is we bring the tap device up, we put the tap device as well as ETH0, which actually is the interface connecting us to the 10-something network, both into promiscuous mode, and then what we do is we are creating a bridge called MyBridge using BRCTL, and we are adding the interfaces tap0 and ETH0 to this bridge. So we are creating a bridge connecting ETH0 and tap0. We then remove the IP addresses from both of the interfaces, and we assign a new IP address, which actually is the one that we before had assigned to the Ethernet interface, 10.421, to the bridge itself, and start OpenVPN. So that's basically all that we need to do. Let's check at how this looks in practice. Okay, we've started VPN here. Let's go to the client side. Okay, and as you see here, we've completed our OpenVPN setup now. So, OpenVPN setup is completed. Let's check what happens once we start to establish a connection. So let's start a packet capture, and let's run something on the client side here. So I'm running, and here is what we were observing with the sniffer. What you see here is we see a connection between 192.168.1.100 to 172.16.2.5, which is again going through the VPN from the client now to the server. Now this is what was about to be expected, I guess. You might be surprised as to why is this machine right away using the tunnel and we don't have to fiddle around with the routing. Well, it's not that surprising because we're basically using a VPN connection on the data link layer. And as you see here now, if we look on the client, we are no longer using the 192.168.1.100 address, but we are actually using the 10.2.4.2.1.2 IP address for connecting to the server. So again, as viewed from a server perspective, and as we mentioned for remote access VPNs as well, this machine now virtually is using an IP address from the intranet where it is connected through with the VPN. So basically this machine now is part of this network here and uses the address, as you can see, 10.2.4.2.1.2, which, if you remember, we assigned beforehand to the respective interface that has been set up. We can also take a quick look here at the routing table on this machine. Here it is, and what you see here is we have 10.2.4.0 network, and everything into the 10.2.4.0 network will now go through the device tap 0. Exclamation mark, as you can see here, we are basically using something that's akin to split tunneling, because everything we don't know where it's about to be sent is going to 192.168.1.5 now. So any other connection would not be going through the VPN, and I'll leave it up for you to think about how we could correct this by modifying the routing table, and maybe you can also try this out in the lab. So that concludes the practical demonstration of OpenVPN as a remote access VPN with a tap device. So let's take one step back and look at VPN technologies and their classification. When we considered IPsec, we basically studied one way of implementing a VPN solely on the networking layer. The packets that were received and delivered were basically received from the networking layer at one endpoint and delivered to the networking layer at the other endpoint. Of course, these layers need to coincide, and the way the packets were transported were by transporting them on the networking layer. So IPsec was a VPN implementation completely based on the networking layer. But when we studied OpenVPN, we already found out that there are alternatives how this could be done. So for instance, with respect to how the data is transmitted between the endpoints, we saw that with OpenVPN, this is basically a protocol based on TLS-SSL, which means that the protocol operates on the transport layer. So there are processes running here and there which would get the data and then do something with it. We've also seen that the data which goes into the VPN, the data which is received and where the data is to be delivered, need not be bound to the networking layer, but could also be sent from the data link layer. So with OpenVPN, if we are using tap devices, then the data is obviously coming from the data link layer. We are sending putting frames in here, and we are putting frames out on this side. So in general, there are two types of features that can be used for classifying a VPN. One is where the data is received and to which layer the data is then delivered. So on which layer is the data received, on to which layer is the data delivered. Of course, that's always the same layer. And the second classification feature is the question as to how the data is transported between the two endpoints, aka the technology for the secure data transport between endpoints. So that is a general classification of VPNs, and it is a good idea to study, if you have a new VPN technology, how the technology works by looking into these features. Let's move on to risks when using VPNs, and one of the risks when we use a VPN is so-called split tunneling. Well, first question is, what is split tunneling? What's it all about? Well, so far we've only used VPNs as a secure means on accessing private networks through public networks. But there are risks associated with running VPNs that we are going to study in the following. If we're using a remote access VPN, then basically the end system or the VPN client, if you want, which runs the VPN virtually becomes a part of the intranet. However, of course, the machine isn't really in the intranet, and very often the resources which are being accessed from the machine is also not limited to what actually is in the intranet. In fact, it is typical that even if a VPN client is active, then there are a lot of resources on the internet which are used from that client. And if you think about this from an efficiency perspective, it doesn't seem to make a lot of sense to use the VPN for these types of connections. So just assume that somebody is accessing company network with a VPN client from abroad. Let's just say the person is in the United States and the company happens to be in Germany. So there is a VPN connection, client to server, from the United States to Germany through an encrypted tunnel. Now assume that that person would like to check the bus schedule in the city where he currently is, and for doing that, what happens is that if I'm using the VPN, first, if all traffic is routed through the VPN, traffic would go to the VPN server to Germany, and then from there through the firewall back to the server in the States. And as you obviously see from this example already, that could have a high impact on latency, response times. It's not the most efficient way of doing it. It seems much more efficient if only those connections which really need intranet access would go through the VPN, and all other connections are routed directly to the internet. And this is known as split tunneling. Split tunneling comes with a grave security risk because the client that runs the VPN in this case has two logical interfaces, one which is directly connected to the internet and another logical interface that actually is connected to the VPN tunnel. And even though this is only a logical interface, routing between the two can be enabled. And if routing is enabled, then this is what can happen with split tunneling. An attacker may send something to the public interface of a machine, and then this machine acts as a router and forwards the traffic from the attacker through the established VPN connection into the internet or wherever. That basically means that this machine here, the machine running the VPN, becomes a security risk, because if somebody happens to be able to break into machine, activate routing, and this machine is basically a machine outside the intranet that could be used to hack into the intranet. That's why split tunnels and split tunneling should not be used for security purposes, and it definitely is the case that most VPN connections for remote access would not allow split tunneling. There is another thing that I'd like to mention. Using public networks for accessing resources comes with a risk. If you're using a public network, then before the VPN is active and you are looking at a web page, you are enabling a connection, then if you have, for instance, a router and you are not using encryption, you don't have the VPN established yet, then if you are accessing a web page, even if it's the right web page, when the page comes back, the page can be, if it's unencrypted, manipulated on the router, and as you see here, indicated by the M here, malware might enter your machine through the public network if there is no VPN established. And even if you want to establish a VPN, it's usually the case that you don't establish the VPN right away, and this comes with a risk of an infection for the machine. Particularly, it also comes with a risk that the machine gets infected while the VPN is not active. So if you're using a VPN and if you have a policy to establish a VPN, it might make sense to establish the VPN as early as possible or to force users to establish a VPN. So again, in other cases, it is possible that machines might get compromised by malware. How well the user is accessing, let's say, his or her favorite website. He has accessed this website 1,000 times before, and it actually is access to the right site. So what comes back is the actual original page, but this here is a public router under the control of an attacker. The attacker injects malware into the very page which was delivered by the server, and this is then handed back to the machine. And again, this is the page that has been requested from the site where it has been requested from, but now all of a sudden it contains malware and can infect the client. And if this happens, of course, once the machine is infected by malwares, VPNs don't offer any type of security, because basically whatever goes through the VPN is compromised to begin with, because it ends up on a compromised machine. So let's summarize what we did today. Virtual private networks allow the use or allow to run a virtual point-to-point connection that is secure over a public network. VPNs are typically used to either allow remote access to clients on the internet, to intranet resources, and basically transform these clients into virtual, or to relocate these clients virtually into the intranet. Moreover, it can be used for a site-to-site VPN in which two sites are connected by a virtual private line that is actually implemented over a public network. We looked into two types of technologies, how VPNs can be facilitated. One was IPsec, the other one was OpenVPN. And we also looked into a general classification scheme for VPNs that is based on where the data is, where the data comes from which layer, and to which layer the data is delivered, and how the data is actually transferred between the two endpoints of the VPN. Moreover, we discussed risks that come with the use of a VPN. And that concludes today's lecture on VPNs. See you next time.